Hello. Uh, I am I audible? I hope I'm audible. So it's 7 o'clock. Um, let's start today's session. So as usual, do you have any doubts regarding the previous year assignments or the course content covered till now? Yes, Zaman. Kabir Zaman. Actually, you no need to raise the hand. It's interactive. You can switch on your mic and you can ask me anytime. Actually, I'm not able to hear you. Meantime, let me check my recording. Okay. Hello, Kabir. Uh, My volume is full, but I couldn't hear you. Were you talking? Okay, okay, okay. Take your time. Take your time. Uh, all right. In the meantime, if anyone else have any doubts, they can ask.
Yeah, hello, Mr. Ganesh. This is Srilakshmi here.
Hello.
Yeah, so is this session for week six, right? This is for discussing week six assignment questions, right?
So basically, if you think week six assignment quest, it's not like that. You can ask me questions about anything till week six. Week six assignment questions are supposed to be due coming week, right? So I cannot discuss the solutions for that. Uh, Maybe I can give you a clarity if you have any doubts, but you can ask till week six content. Yeah.
Okay, okay. Yeah, because in week six, 22, right? Question number 22, it says moles of requires liquid. I don't know if it should be liquid oxygen in one case. So I just wanted to check if that was a typo.
Okay. Let me open it. Which question is it? 20,
22.
22. Okay.
Yeah.
A cryogenic rocket propellant question, right? Comprising liquid oxygen for
Yes.
oxidizer and liquid hydrogen for fuel is used in rocket. Mixture ratio is 6.4. Determine the following. Moles of LH2 required per mole of LH2 expression. Yeah, yeah. I think there is a typo. It should be moles of LO2 required per mole of LH2, right?
Okay, so first one is
One mole.
LO2. Right?
So
Most of
for one
LO2.
mole of fuel, how many moles of oxygen required? So that is how we calculate.
Okay. Okay, okay. Okay, thank you.
Zamam, you're back. Still, I cannot hear you. Still, there is a problem, I guess. Okay. So does anyone else any questions?
Yeah, I actually had a question on week five.
Yeah.
Yeah, I think it was question number 25.
Okay.
So I
Let me.
know sir had responded to that, but I could not understand it. So if you could please explain that, that would be helpful.
Okay. Okay. So it's question number 25. Uh, A contour nozzle of same ratio as a conical nozzle is less prone to flow separation due to which of the following? Okay, higher expansion in the later part of divergent compared to conical nozzle, slower expansion in later part of divergent compared to conical nozzle, and shock wave formation in the divergent. Answer is higher expansion in the later part of divergent compared to conical nozzle. Okay, um, sure. So you understand how flow separation happens, right? So flow separation happens only if there is a uh, when it is an over expanded nozzle, right? So when you have say a CD nozzle like this, uh, when you say you are expanding, right? So let's say this is the pressure versus okay, Zamam also have the same question. All right. So this is the pressure versus X curve. Okay. Um, and your nozzle expands to an exit pressure PE. Okay. And you have an ambient pressure PA. Right. So when PE is uh, if you say if it is less than PA, okay, then it is an over expanded nozzle, right? Because you over expanded the I mean you over expanded it, exactly, right? So what happens at the divergent portion? One second. So this is at mark number equal to 1 or throat. So at the divergent portion, what happens? It is a supersonic flow. So basically, you don't know the downstream condition. So sudden high pressure, let's say this is PA ambient, okay. So you should expand till P exit, but your exit pressure is I mean the ambient pressure is PA, so the flow doesn't know, but it has to adjust, so it has to put a shock wave. So sudden there will be a abrupt discontinuity in there. So basically what it does is it puts on shock wave, and then it reaches the mm, let me draw it in a different color. So basically, it won't expand till PE. Instead, it puts an shock wave, and then it reaches ambient. So that is what it has to do. But sometimes what happens, putting a normal shock wave might require very high pressure gradient, so it won't put. Instead, what it does is it creates an oblique shock. So in this case, uh, it creates an oblique shock. Okay. So when it creates oblique shock, or let's say, like what we no need to know whether it's oblique shock or normal shock, but anyway, what's going to happen is the pressure is going to rise and reach the ambient pressure. Okay, so to have clarity, uh, let me rewrite this to let me exaggerate the situation. Let's say I have ambient pressure is here. Okay, so I have to reach this ambient pressure. So what I have to do is I will put some I will put a shock, and then I will reach this ambient pressure. So what happens whenever there is a pressure gradient, that's that way only flow has to take place, right? So in this case the pressure gradient is in this direction. Okay, there is a low pressure, so flow will actually takes place in this direction, but there is a shock, and there is a uh, the pressure gradient has changed, which we call it as adverse pressure gradient. Because of that, there is going to be another flow happening in this direction, right? So this causes the flow separation in this zone. So basically, if I want to write here, the flow will separate, and then it becomes like this, right? So having understood that how flow separation happens, so you need a adverse pressure gradient in order to have a flow separation. Okay, and that adverse pressure gradient will be you will get only when there is a over expanded nozzle. right? If not, you won't get a adverse pressure gradient and you are not going to get flow separation. And uh, so what the question says is, so so the flow separation is mainly due to inadequate velocity of the boundary layer due to adverse pressure gradient. So basically, boundary layer doesn't come into picture here. Uh, Boundary layer is there. See, boundary layer is there everywhere. Okay, so along this nozzle there is a boundary layer, but uh, the flow separation is not mainly due to that. The flow separation is due to um, the competing pressure gradients, right? So one pressure gradient is accelerating the flow towards, and there is another pressure gradient which wants flow to happen in the opposite manner. That causes the reversal in flow, right? So the if you think about boundary layer, so actually you cannot think about boundary layer here. You know why? Boundary layer needs usually you need to consider viscosity terms. Uh, One second. So, Kaviyasan, do you have? Uh, can I come to your question later?
Yes, sir.
So yeah, thank you. So what happens is, in order to have a boundary layer, so in the boundary layer, what is important is viscous effects, right? So in 1D analysis, we didn't do any viscosity. Uh, we didn't take into account in the viscous terms. So nevertheless, but there is going to be a boundary layer in the nozzle also. But these boundary layers will be um, yeah, it's going to be so boundary layer indeed affects the flow separation, but the major contribution for this flow separation is because of this adverse pressure gradient, right? This adverse pressure gradient is not caused due to the boundary layer. So due to inadequate velocity of the boundary layer. So what do you mean by inadequate velocity of the boundary layer? So boundary layer, I don't. So let's say if you want to draw a boundary layer, this is what a boundary layer looks like, right? So if you want to draw a velocity profile, it's going to be zero and there's going to be this thing, right? So here also, if you need a flow separation, let's say, okay, so here also there is, this is a flat plate, let's say, right? If you need a flow separation, there should be an opposing flow happening on the opposite side, which causes the boundary layer to detach, right? So let's say, for example, if you take a ball, okay, this tennis ball, so that's the usual flow separation scenario we used to see, right? So here, if you see, the boundary layer is going to form like this, right? So flow will happen like this, boundary layer is going to form like this, but what happens, due to the change in the shape, okay, the shape is curved, right? Due to change in the shape, there's going to be pressure difference. The pressure here is going to be high, right? But the flow is happening this side, flow is in this side, but the pressure gradient tells that flow should happen this side. This is the adverse pressure gradient due to the form of the sphere, right? So what happens at this place, at somewhere in the downstream, there the boundary layer is going to separate, the flow is going to separate from the ball. That's the recirculation of the flow. It's so which case you are telling, the ball one, you are telling recirculation. Okay, so here you are telling it's going to be in recirculation zone. What do you mean by recirculation? So Recirculation is something different, right? So when do you say recirculation? Whenever there is a flow turning happens, right? So um, let's say you have something like this, okay? So at that time, flow has to detach from here and it rejoins here, and in this place there is going to be recirculation, right? Here, these are vortices, right? I'm not talking about vortices. I'm talking about separation of flow, right? Vortices comes after. So here vortices comes. Vortices comes after flow is separated. Without separation of flow, you cannot have vortices. Flow, in order to flow to separate, you need a, so not sure sir explained it in the discussion forum. Flow separation takes place at the walls of the nozzle due to adverse pressure gradient. The wall boundary layer in the conical nozzle does not have adequate velocity to overcome the adverse pressure gradient. Unlike in the contour nozzle, we did not consider viscosity of flow in the lecture. Right. So, hmm. It is true. The does not have adequate velocity to overcome that. Yeah. So basically, when there is a two composing pressure gradients, so this if this pressure gradient is more, the flow will be at high velocity, which does not allow this pressure gradient or this flow to happen. That is what it means when there is no adequate uh, boundary layer velocity which will uh, tackle this adverse pressure gradient, right? If it cannot tackle this adverse pressure gradient, there is going to be flow separation. So that is what it means. When the opposing flows pressure gradient has to be uh, the that effect, the pressure gradient effect on the due to the adverse pressure gradient effect should be overcome by the uh, advancing flow or the upstream flow, right? Then what happens? There won't be any flow separation. If there is a opposite, if that adverse pressure gradient, if your flow cannot tackle, then there is going to be a flow separation, right? So that is what here also does. There is this adverse pressure gradient, but what it can does is it can decelerate the flow to zero, but this pressure gradient didn't decelerate to zero. In addition, it went one step further and it reversed the flow. That is what called flow separation, where that's when it got when the reverse flow will happen. At that time the flow separation takes place. That is what SAR must have meant. And there is a boundary layer, yeah. So yeah, so inertia of, yeah, flow facilitates or prevents the flow. True, exactly. So when you have high inertia of flow, when you have a high velocity and you cannot be stopped, okay, or the force acting opposite to you, it cannot stop you. There's no flow separation is going to happen. So basically, what it means is the effective pressure gradient is going to be in this direction, so that flow happens. If the effective pressure gradient changes the sign, okay, when I say effective, the forward pressure gradient and the adverse pressure gradient, when you add these two, if the effective is going to be along the direction of flow, there's no flow separation is going to happen. When it changes the sign, at that time flow separation happens, right? So based on this, which option should be correct for question for 24? Okay, so boundary layer of nozzle divergent being at lower velocity and inertial forces so what it says is flow acceleration in a conical convergent divergent nozzle takes place for nozzle exit pressure much lower than the ambient pressure, right? Uh, due to takes exit pressure much lower than the ambient pressure, flow separation conical convergent divergent nozzle exit pressure much lower than the ambient pressure due to uh, boundary layer on the nozzle divergent being at lower velocities. No, you okay. So not say boundary layer on the nozzle divergent having low velocity, right? So um, the boundary layer is always going to have low velocity. So if you look at it here, it's going to be zero. and here is going to be reach u infinity, or let's say it's going to be 0.99 times u infinity, right? And you know u infinity section is going to be very high because it's a supersonic flow, right? So you cannot say because of low velocity, so in boundary layer anyway it's going to reduce it to zero. It is not really due to velocity, but it is rather due to adverse pressure gradient, and the inertia forces cannot tackle that. That's all. So flow separation takes place for nozzle exit pressure much lower than ambient pressure due to the inertia forces accelerating the flow. Inertia force is going to accelerate the boundary layer of nozzle divergent being at lower velocity. That is, see, that statement is little ambiguous. Uh, see, yeah, inertia force. So, okay, but the inertia force cannot be the answer as it prevents the flow separation. It is true. It prevents the flow separation, but uh, the other statement also doesn't tell you anything about flow separation. Boundary layer on the nozzle divergent being at low velocity. So there is no. Okay. Both options are not correct for this ambiguous questions, right? So I too feel like that. Yeah, let me check. So what it says is flow separation in a conical convergent divergent nozzle takes place at nozzle exit pressure much lower than ambient pressure. That is true. Nozzle exit pressure will be lower than the ambient pressure due to the inertia forces. Flow separation cannot happen due to the inertia forces accelerating the flow, right? Okay. Are the boundary layer on the nozzle divergent? Okay, let me check in books. Just give me a minute. Forces available in the superconducting panel delay the process of flow separation to the pressures much below the ambient pressure. So actually, inertia forces will delay the process of flow separation, right? So it can separation. That is true. Uh, Slower than the ambient pressure. What does question say? So takes place on the nozzle exit pressure much lower than the ambient pressure process due to inertia forces. Flow separation takes place. Okay, okay. Okay. See, yeah, I see there is a. I feel some subtleness in the question. If you look at the question quite carefully, so it says flow separation in a CD nozzle takes place for nozzle exit pressure uh, much lower than the ambient pressure. So basically, let's say it takes place at uh, still there is a problem. Yeah.
So one quick comment, like I'm just looking at my notes from the lecture with Sir. So in that, what it says is this is actually I have documented this under the Summerfield criterion. Okay,
Yeah.
so what I have mentioned in my notice in the ground when the ambient pressure is let's say 100 kPa, we don't
Mhm.
have to keep the exit pressure also as 100 kPa because of the Summerfield criterion. We can afford to keep a much lower exit pressure and the initial inertial forces help to delay the flow separation.
Exactly.
So
So
I think the question is all in the same way, right? But I mean, it's the same thing which is asked in the question, but in a different manner. That's what I feel.
yeah, so that is what I also feel. Uh, so the flow separation usually happens at some pressure, exit pressure. So it will be much delayed when you have inertia forces accelerating. Um, I think that is what meant while asking that question, but it is not quite coming straightforward. The question is not coming straightforward. Okay, let's not worry much about it. I will look into it, into the or I will talk with professor about this question. I think it's 25, right? Yeah, 25 is still remaining. This is this is 24. Okay, there's a problem with 24. And about 25, 25 is what you asked, right? I think I didn't remember the name. Yes, Sen? Yes.
Yeah, so 25, my question was, so in the case of contour nozzle, right, it has a higher expansion in the initial divergent portion and then the expansion is lower at the exit. Right, so that is why I thought that it is less prone to flow separation because the pressure difference is less in the exit portion.
So in the contour nozzle, yeah, conical nozzle it's simple. The contour nozzle initial divergence angle is more. So and later the divergence angle will be less. So the flow separation to happen in contour nozzle it does not happen because okay. So in the contour nozzle, what happens is it has larger initial divergence angle. So here the pressure is large, right, and here the pressure is less. So this is let's say high pressure, this is low pressure, and let's say in the conical nozzle, it's going to be like this. So this distance is going to be smaller, and this low pressure is going to happen somewhere uh, in the middle. Okay, so the place where this P low is, it's where flow separation happens. Let's say if you consider it like that. Okay, so here it should happen much before, but still, but since there is a the pressure gradient, as I said, the pressure gradient in this uh, the contour nozzle is going to be very high initially, right, in the initial region, which does not allow the pressure, does not allow flow separation to happen, but it might delay it to some other P low dash. Okay, so that is the reason the contour nozzle is less prone to flow separation. So if we look in this manner, there's going to be higher expansion in the later part of the divergent compared to the conical nozzle. Okay. Higher angle at the beginning portion means greater expansion, right? Yeah. Actually, it's true. Yeah. Higher angle at the beginning means you have more divergence, you have more area ratio is or let's say area is increasing very fast, right? since area is increasing very fast, pressure is going to velocity will rise very fast, so pressure will decrease very fast. So there's going to be higher expansion initially, right? And then yeah. So did you ask professor what did he say? So maybe I will also have the email. Um, so there is okay, this one 25. A contour nozzle expands the flow along the nozzle wall at a slower rate compared to the conical nozzle with respect to distance towards the exit of the nozzle. The possibility of having higher value of adverse pressure gradient is therefore less. Contour nozzle expands the flow along the nozzle wall at a slower rate compared to the conical nozzle with respect to distance towards the exit of the nozzle. Respect to distance towards exit of the nozzle. Okay. This is the exit. Yeah, that is true. But in the question, it's been asked that higher expansion in the later part of the divergent compared to the conical nozzle. It should be slower expansion at the later part of the divergent. Okay. But yeah, whatever Sir wrote is also right. From the exit, if you see, the pressure is going to increase gradually initially, and then it's going to reach a higher pressure at the throat. And if you go from the throat, it's going to be higher expansion near the convergent part and lower expansion near the divergent part. So it should be basically slower expansion at the later part of the divergent. Actually, you know, that is the result of nozzle geometry. In fact, the main reason is uh, you will achieve that pressure well before in the initial region of the expansion, which makes the pressure gradient to be higher than the adverse pressure gradient, and that is the reason you are going to reduce the flow separation. Yeah. Yeah, it makes sense. Maybe, yeah, again, I will talk this also with professor and I will let you know. Ha ha. So, yeah. So, actually, what Sir wrote is also exactly matches with the other option. The smaller expansion in the later part of divergent compared to the conical nozzle. So, I'm not sure. I will let you know. I will talk to professor and I will let you know.
Okay, thank you.
Is there any more questions? Okay, you asked another question, question 22. What about question 22? Okay. So the same assignment? Is it the same assignment? Okay, okay, okay. Thrust developed in the rocket has two components, momentum thrust and pressure thrust, and the nozzle exit pressure. Okay, let me read the question. A contour nozzle developed with optimum expansion of ambient pressure. Facilitator ambient pressure is 0.02 megapascal. So nozzle is going to expand for 0.01 megapascal, but my ambient pressure is 0.02 megapascal, right? So basically, I'm going to have over expanded nozzle. That is true. With the thrust developed in the test facility will be greater, less, or equal to. Okay. So hmm. So you have a over expanded nozzle. If So it is not clear which thrust. Okay. Anyway, so if you look at the thrust equation, it's just going to be m dot into VE plus PE minus PA, right, into exit area, right? So when PE is greater than, when PE is less than PA, that is the case here, right? So what happens is this is going to be negative. So your overall thrust reduces, right? But it has given that it's greater. Okay. And Sad told the thrust developed in the rocket nozzle has two components, momentum thrust and pressure thrust. When the nozzle exit pressure is same as ambient, we have maximum thrust for which the thrust coefficient of nozzle is maximum. That is true. The pressure thrust is zero. True. This is because the pressure thrust decreases more compared to the relative increase of momentum thrust. Okay. Yeah. So this part is momentum thrust. This part is pressure thrust, right? So usually in a overexpanded nozzle, what happens is good question. Basically, if you look at it from this formula, you are going to get less thrust. Yeah. Let me ask, Yasin, do you have any thoughts on this?
Yeah, so I had marked the so this 22 is a subsequent question of 21, right? So I had marked 21 as under expanded, and
Okay.
that is why I marked 22 as greater. So 21
Okay.
was incorrect for me,
Okay.
but
Okay.
22 is correct.
So
So
you understood why it is overexpanded, right?
no, no, I didn't understand that.
So so you know what is overexpanded nozzle, right? Um,
Correct. Yeah. The exit
so
pressure is less than PA.
So that is because exit pressure is less means you have expanded more, right? Um,
Correct.
expansion more expansion means from higher pressure to, so expansion is nothing but decrease in pressure. So you decrease the pressure to a larger extent. That's why it's over expanded. So in the question, what it was said is um, the nozzle is designed for ambient pressure. Nozzle is designed for an optimum expansion at for an ambient pressure of 0.01 megapascal, which means that my exit pressure will be 0. If my exit pressure is 0.01 megapascal, then I'm going to have optimum expansion, right? uh, but uh, so so my nozzle is always going to give me exit pressure to be 0.01 megapascal. Okay. Now if my ambient is 0.01 megapascal, then I have perfect expansion. Now what they said is in the test facility the ambient pressure is 0.02 megapascal, right? So if you compare these two, so here PE, which is less than PA, right? So my nozzle will have a exit pressure of 0.01 megapascal change. But my ambient is 0.02 megapascal, which means compared to ambient, I have expanded more. That's why it's over expanded nozzle. Is that clear?
Okay, okay, okay. Yeah, I got it now.
Yeah. So if you do that, the overall thrust actually reduces. I'm not sure why it is marked greater. We know is the under expanded nozzle is always going to give greater thrust because its exit pressure is higher. Um, what do we mean about it? So okay, in a separated flow, so provides high pressure at the nozzle, therefore the nozzle to the altitude. In the book also, it was told that in separated flow, it would be helpful because there will be a high pressure gradient. Therefore, the nozzle can adapt to the altitude, and the thrust from the nozzle with flow separation is more than the thrust corresponding to the same area ratio for which flow separation has not take place. So, basically, there are two ways to think about it. If you consider flow separation, because it's an over expanded nozzle, you can consider flow separation. So, if you consider flow separation, what happens is you are going to again, there's going to be adverse pressure gradient, there's going to be shock, and then this shock will make your pressure to reach ambient pressure, right? So you can reach ambient pressure, mm, or higher pressures. So the higher pressure can lead to pressure. Yeah, I'm not sure. This is also quite confusing. Okay, this is also confusing. Yeah. Okay.
So I was just looking at the question again, Mr. Ganesh. So in 21, right? So if I think about it again, right? Like, so initially in the when it was designed for 0.01, right? And then when it was tested, it is actually tested for 0.02.
Ambient pressure is, yeah.
Right, right. So basically, it is the PA is greater than PE, right? In this case,
PA is greater than PE.
PA is greater than PE. Okay, okay. So that's why it's under.
It's that's why it's over expanded.
Sorry, yeah, overexpand. Okay.
So yeah, this is also confusing. True. Uh, why the thrust should be greater? Yeah. Okay, I will think about it. I will, if possible, I will talk to professor. Um, what Sir wrote? Sir wrote, they say there's a whatever Sir wrote is also right. So the thrust is going to be, there's going to be momentum thrust. There's going to be pressure thrust. When the nozzle exit pressure is same as ambient, we are going to have maximum thrust. The thrust coefficient is maximum. True. The pressure thrust is zero. That is also true. But all these things are when ambient matches the exit pressure, and uh, the, the pressure thrust decreases more compared to the relative increase of momentum thrust. That is also you can consider it, but none of this answers the question. Okay, yeah, no problem. I will look into it. I will let you know what are the solutions. Is there any other questions also like this? Are others fine? Please and thrice. Please reconsider 22, 24, and 25. Yeah, yeah. Sure, I will. Yeah, I will talk to professor. Let me see what he tells about it. Sure. So there is one more. So how it will be over expanded? I don't know whether Angel is here. Uh, okay, he's not here. All right. Uh, J is minus V by PA. Yeah, true. M dot Vj should decrease. So ideally, if you see what happens is in a over expanded nozzle, since you have a shock, there are actually different ways of viewing it. There can be a oblique shock here, right? There can be an sorry there can be a normal shock. If it's a normal shock, this side is going to be subsonic, and if it is subsonic, your Vj is fully reduced, so there's not going to be any thrust you are going to gain. If it is a oblique shock, if it is an oblique shock, your analysis stops right where the expansion ended. Okay. And whatever your analysis, actually your control volume, if you draw the control volume for this rocket, it's going to end here. So this would be the rocket. So all these oblique shocks, all these things will happen here, right? And then there's going to be expansion waves, all these things is going to happen here. And but your analysis actually ends here. Here you say PE is less than PA. Because of that, there's going to be pressure thrust, which is going to act opposite if it is an over expander. If it's going to act on the other side if it is an under expander. Uh, but if there is a normal shock inside, which means that you have very low pressure gradient, there's going to be subsonic flow after it, and the subsonic flow is actually fatal to the expansion. So if you have subsonic flow, you are not going to get any thrust, right? So that will happen. Uh, yeah, but I will look into it, all these three questions, and I will let you know. So, is there any other questions? Any other questions like this? Do you have any doubts? Caviers and rather explain flow separation in about some 5 to 10. Because flow separation was a big leap in terms of conceptual understanding compared to other concepts. Caviers, do you still have doubts? Do you want me to explain it again? In Caviers message. Okay, okay, I will explain to you why the flow separation happens. So let me, what example I can give. So there are multiple forces comes into play when you talk about flow separation. Let's say, for example, uh, let's take Gulf ball itself. So one would be smooth ball, and so basically what happens, there's going to be flow, right? So when there is a flow happens, my flow is going to happen like this, u infinity, right? So here what happens, I am going to, since ball is stationary, or let's say if you stay inside a ball and if you look at how the fluid flows around, okay, what happens is, due to non-slip condition, there's going to be a zero velocity here, and it's going to reach some velocity through a thickness, right? So that is how boundary layer will be developed. So here the boundary layer will be developed something like this, right? Something like this. Now what happens, this keep on, it cannot keep on developing, because there is a the pressure, the velocity is going to come and stop here, right? So this is a stagnation point where the pressure is going to be very high. Okay. And similarly, because of this turning, or because of the curvature, we call it there is form drag. So basically it causes a pressure difference, which is actually pressure drag. Okay. So because of this, there's going to be high pressure here also. Okay. So fluid flows from high pressure to low pressure. So what happens from here, fluid goes like this. Okay. Ideally it has to go like this, right? Really it has to go like this. But what happens, there won't be enough support for the flow, because there are two pressure gradients acting. One is which is facilitating the flow to happen like this, which we called as favorable pressure gradient. Okay. There is this high pressure here also, which which makes the pressure to which makes the flow to go in the opposite direction. We call it the adverse pressure gradient, right? So I'm just giving you in a simplified explanation why this happens, but there is a lot of uh, concepts goes into it, because there is a basically it is due to the pressure gradient for which the flow separation happens, but it also has to do with the geometry of the object, because geometry is what creating the pressure difference and allowing the flow to happen. So yeah, so that is due to the geometry. So let's say if let's say consider a fan. You have a fan, right? So a fan is moving. Why does a air is coming down why does air flows down, right? So if you think about it, why does air flows down? Because of the geometry of the due to suction. Suction, what is suction? There is going to be a pressure, right? Due to the geometry of the fan, there's going to be pressure which will be in the other side of the blade, which sucks the air in it. Okay, so that is the reason air flows. Similarly, here also, here there is going to be there's going to be a adverse pressure gradient due to the change in the uh, geometry. So basically, if you have a geometry like flat plate, there's not going to be any adverse pressure gradient, right? So let's say a flow is happening like this. Now the flow is fully accelerated in this direction, okay, and I have to maintain a not no slip boundary condition here. It cannot go wrap around it and then it can go out, right? So there is a one force which is accelerating in this direction, on the positive direction. Now it has to leave the surface, because then only it can go to the downstream, right? So in order to leave that surface, there should be a flow separation happening, and in order to have a flow separation, there's going to be an adverse pressure gradient, and because of this adverse pressure gradient, this flow will separate and it reattaches at later point. Okay, so you can, yeah, so basically due to the pressure gradient, and this pressure gradient is due to the geometry of the uh, bluff body or blunt body which we deal with. Okay, so uh, mm, yeah, so that is the reason we have this flow separation. Okay, uh, it is due to these opposing forces coming into picture. So for example, if you take a nozzle also, uh, so in the nozzle you are getting accelerated along this direction, right? And I am suddenly generated adverse pressure gradient which is going to happen in the opposite direction. So that is due to the if you plot the um, let me take another page. So what I told was so I'm going to have a, if I have, this is not the right plot. So this is the pressure and this is the position Ex. If I don't have exit pressure to be ambient pressure, what I'm going to have is I'm going to have a shock, and then due to shock I'm going to have a subsonic section, and in the subsonic section, what the velocity is going to subson I mean so let me draw a nozzle also so that it will be clear. Okay, so this is divergent portion, right? So divergent portion, subsonic. So if you have a subsonic flow in a divergent portion, velocity is going to decrease, pressure is going to increase, right? So that is clear. Now if you have a, since you do not have the exit pressure to be same as the ambient pressure, uh, and you have accelerate to supersonic. So um, this is Mach number plot, okay, and okay, so So this is Mach number plot. At the throat, you know Mach number is equal to 1. Okay, so this corresponds to Mach number equal to 1. Okay, now you have to expand further, because as a divergent section, subsonic flow means velocity is going to increase and pressure is going to decrease, right? So pressure keeps on decreasing, but since it's a supersonic flow, it doesn't know the ambient pressure. So in order to uh, uh, reach the ambient pressure, it puts a normal shock. Okay, and that normal shock keeps on moving forward as the pressure gradient increases, and it becomes oblique shock later. But let's say if you consider just a normal shock, okay, so basically shock is nothing but discontinuity. Suddenly the pressure rises. So when the pressure rises, after a normal shock, it's always a subsonic flow. If you know what does normal shock does is, so it changes this it across a normal shock. This side it will be supersonic, the other side it will be always subsonic. Unlike oblique shocks, in oblique shocks you can have a supersonic and supersonic downstream also, but in normal shocks you cannot have a supersonic downstream, because it just stops the flow and makes it subsonic. Okay, so when it makes it subsonic, and you know what happens in the divergent part, in the divergent part pressure is going to increase. So this, there will be a increase in pressure. Okay, and it's going to reach, this pressure is going to be P ambient. Okay, so this is what it does. So basically, if you have a over expanded nozzle, my exit pressure is lower than the ambient pressure, and I have accelerated to supersonic. In order to reach the ambient, I have to put a normal shock, and then I will reach the ambient. And if you look at this, here the pressure, this side the pressure gradient is negative. So or the flow is likely to happen this manner, right? So let me take a green color. So since the dp by dx is less than 0 along this direction, the flow is likely to happen in this direction or towards the positive x, right? But here the pressure is increasing, the pressure is high at the ambient, and then it reduces to a lower value at the shock, right? So at that time there's going to be another pressure gradient, which is dp by dx, which is positive, right? So this is the adverse pressure gradient. This is what we call it, adverse pressure gradient, because it's in the adverse direction of the flow, or in the negative, or in the decreasing direction of x. So what happens, this dp by dx, so this dp by dx, it accelerates the flow, and this dp by dx will make the flow to go in the reverse direction. So what happens, so at some point of time, this dp by dx is overtaken by this dp by dx. Okay, so this will be higher and this will be lower. At that time what happens, the flow separation takes place, and there is going to be a flow reversal happening here. That's what happens, and that is the reason there's going to be flow separation, because of this additional pressure gradient. But explaining flow separation, so this is just to introduce the concept of flow separation. There is a lot of research just only in flow separation. Okay, and there are a lot of aspects which affects the flow separation. So it is in a simpler terms, I'm explaining in terms of adverse pressure gradient, and there are, yeah, sure. Can I interpret that due to normal shock pressure? Yeah, pressure is actually you can say adjusted, but instead what you can say is the pressure has to reach the ambient pressure. Okay, so that is the reason it puts a normal shock. So you do not know the downstream condition. Okay, when you are accelerated to supersonic, there is no information which comes from downstream to upstream, right? So pressure is what is pressure? Pressure is nothing but our sound, our pressure, whatever. It's sound and pressure are same. Sound, the pressure disturbance is what we call as sound. Okay, that's why the speed of sound comes into picture when we deal with nozzle. So when we are accelerated to high speeds, the downstream, you won't receive the pressure disturbance. Or let's say if something changes in the downstream, the supersonic flow will never know what happened at the downstream, because you are traveling with a faster rate than the information. So information will travels to you at the speed of sound, but you are traveling with more than speed of sound, more than Mach 1, right? Because of that, you do not know what happens at the downstream. So if you do not know what happens at the downstream, it's like you are going and hitting at the wall, right? So if you know wall is ahead, you will take a turn and you will go. Now you have to go and hit at the wall. So when you hit at the wall, suddenly your velocity will be from very high velocity to zero velocity, or let's say less velocity, right? So that is what we call it as shock. The sudden destruction of, or sudden what do you call, sudden reduction in pressure, or sudden discontinuity. Okay, we call it discontinuity because it is not continuous. It suddenly changes from very low pressure to high pressure, and high velocity to low velocity. So actually, shock, what it is it adjusts the flow such that it meets the ambient pressure. That is the reason. True. Because of that, you have adverse pressure gradient, and because of adverse pressure gradient, you have a flow separation. And I'm telling you that only the adverse pressure gradient is not the reason for flow separation. There are various available reasons. Just to introduce you towards the flow separation, it has been explained in a simpler terms. Okay. uh, it is itself a vast field of research. So, does that clear your doubt, Kaviyarasan? All right. So, is there any more doubts? We have to. Okay, I have this doubt. Assignment 4, question 18 and 19. Okay. Let me go back. Assignment 4, question 18 and 19. Okay. Sonic velocity of the nozzle, is that what you're we have to calculate the speed of sound at the throat. We first compute the temperature of the throat using Tt by Tc is equal to gamma plus 1 by 2. How do we calculate the flow velocity at the throat? So flow velocity at the throat mark is 1, right? Flow velocity is equal to speed of sound. How do you calculate speed of sound? Square root of gamma RT, right? Does that make sense? Or did I go faster? So at the throat, Mach number is equal to 1. But there might be the case when M at throat is not sonic. But it has been given, right? It's a ideal expansion process is isentropic with no change. The expansion process is isentropic, right? And it has also been given that expanded to the ambient pressure of zero point 0.1 megapascal, right? So if it is isentropic, so what is the isentropic? What are the isentropic solutions for a CD nozzle? Are you aware of that? So let's say this is the Mach number plot. Okay. So the isentropic solutions are actually if you do not reach Mach number 1, let's say this is the Mach number 1, Mach 1. Okay. And uh, so let me plot it. So there is a possibility that you won't reach Mach 1. Okay. You will keep decelerating to zero, right? This is also an isentropic solution, but you need to note that the pressure it has expanded is not the ambient pressure. It's not zero point 0.1 megapascal, right? So, and if it, so again what it can do is it can reach Mach 1, right? And uh, it can it can go and reach it can again mark, even if it reach Mark 1, there is a possibility there, that's when there will be two isentropic solution arises. One is it reaches down and reaches some exit pressure, okay, and the other is it goes on get accelerated and reaches a exit pressure, or which is equal to ambient pressure. So this is what it's given isentropic expansion. And since it has expanded to zero point 0.1 megapascal, you can take that it has reached Mach equal to 1. That is also okay. So if you, so you were, let's say we are not considering the givens in that question. If you have not reached, okay, you want to calculate flow velocity, right? Uh, Temperature is also wrong. So whatever the temperature equation you have, Tt by Tc is equal to gamma plus 1 by 2. It is considering the assuming that mt is equal to 1. Now, so if you do not have Mach number equal to 1, you have some other Mach number, right? Let's say you are given chamber pressure and chamber temperature, and you are given area, right? And with the area, you know A, and there is a relation, right? Area versus Mach relation. That is an isentropic relation, right? Using that, you can find what is the Mach at the throat. When you find Mach at the throat, you can use be 1 plus gamma minus 1 by 2 m square, right? I believe this is the equation. So you put the Mach here, you get the temperature, right? Once you get the temperature, you find the sonic velocity, and then using sonic velocity, you know Mach number, you know sonic velocity, you can find the velocity of the throat. Yeah, I hope it's clear. There was one more question, right? So it is question 18 and 19. Okay, 18, 19, both are same. Okay. So you understood, right? All right. Is there any other questions? Anyone else have any more questions?
So, Mr. Ganesh, I think initially in this meeting when we joined, you were projecting some question on the screen, right? I think that was related to week 6, right?
Yeah, yeah. So actually, I thought I will solve this question in
Yeah,
front
I
of
think
you.
that would be helpful.
Okay. Alright, so let me start solving this question. Um, So, so if you think about what we did till last week is we actually we analyzed the performance of nozzle, and before that we understood what is the thrust we need. Before that we understood what is our mission requirements. Based on mission requirements, we understood the how much thrust we need, how much what is the acceleration we need, what which and then based on that we try to finalize the nozzle, like how much velocity I need at the exit or what is the pressure I need at the exit. Now, in all these analysis, if you go and see, we would have considered that, or in any questions, if you would have noticed, it's just the given would be chamber pressure and chamber temperature. Now, this week, what we did was we tried to get that chamber pressure and chamber temperature, right? So basically, it comes due to the combustion of fuels, so combustion of propellants inside the rocket motor. So when you combust a propellant, it's going to generate a lot of gases, and um, at high temperature, and because you are constrained it in a chamber, it's going to develop high pressure within the chamber, and based on this high pressure and temperature, your nozzle velocity is going to get affected. Once velocity, then thrust is going to get affected based on that, and because of that you will be uh, based on that you will design your mission requirements. So basically, that is how this course has been progressed till now. So today, uh, actually, what we saw in last week was to characterize the propellant performance, right? So basically, the performance of a propellant are in our case right now it's a combustion chamber. The combustion chamber performance is actually characterized using this C star velocity. So this C star velocity will give us how efficient my combustion chamber is. And do you remember what is the C star velocity dependent on?
It's dependent on TC.
Right?
It's molecular mass.
Yeah, molecular weight of the products or molecular mass of the products,
Mhm.
right? And then for some extent gamma also, right? So basically, uh, we need to select our propellant based on these. We need to somehow optimize these parameters and select our propellant such that we can maximize the C star velocity. So uh, so that is what has been the focus of last week. So based on that, there has been a lot of questions given, and based on those questions, I selected. I took one question from the course book. If you remember, it's also written by the same professor, Rocket Propulsion by K. Ramamurthy. So from that book, I selected one of the question, and I am showing you here. Okay, so basically, uh, so today what we do is we try to find those temperature. Okay, this temperature, molecular weight of the products, and the specific heat. And after finding all this, we will try to find the characteristic velocity. So that is the aim of this question I have here. um, so what we have is we have a fuel rich mixture of dodecane. Okay, so it's molecular the chemical formula is C12H26 and oxygen. So there's going to be the oxidizer is O2 at standard condition is burnt in a rocket chamber at a mixture ratio of 2.6. Okay, and assuming that most reactive hydrogen, let me erase this. Assume that most reactive hydrogen in fuel is initially oxidized to H2O. Subsequently, the carbon present in the fuel is first oxidized to CO and thereafter to CO2. The heat of formations are given. Okay, and then what we have to find is we have to find the moles of all product species. We have to find the molecular mass. We have to find heat of combustion. We have to find, in fact, to find the adiabatic flame temperature, we need heat of combustion. Uh, and then once we found these, we can find the C star velocity. Okay, so let's start. So how do we approach this problem? First is we need to find the moles of product mass. What are the moles of the product species, right? So let me write the C6, sorry, not C6, C12H26, C12H26 plus O2, okay, gives what we know this ideal set of products are CO2 and H2O, but we don't know whether CO will form or not, right? Whether it happens only when there is a unbalanced oxidizer in the uh, or in the propellant side, right? What was given is there is a mixture ratio given which is 2.6. So based on this, how do we find? So this reaction is not still uh, balanced, right? So first we need to balance. Once we balance, we know the moles of product species. What is how much moles of CO2 is present, how much moles of H2O is present, right? So what has been given is the mixture ratio. Mixture ratio is 2.6. So what do we know about mixture ratio?
Mass of oxidizer by mass of fuel.
Exactly. So it's going to be mass of oxidizer by mass of fuel, right? So in this case, oxidizer is O2, right? And so how do we write the mass of oxidizer? It yet.
Yeah, so 32x or something like that, right? We don't know
Yeah.
the number of moles of H2, O2.
So we can write N of O2 times molecular mass of O2 or molecular weight. So we already know what is the O2 mass. So it's going to be 32, right? Similarly, if you want to write N of C12H6, H26, which is actually 1, right? Here you have 1 mole of fuel, and you are going to have what would be the molecular mass of C12H26? Okay, there is an answer 170. So yeah, it is true, it's 170 because when you do this calculation, It's nothing but 12 moles of uh, 12 carbon atoms we have. We know carbon's molecular mass is 12. So 12 into 12 plus 26 is the hydrogen. 26 into 1, hydrogen's molecular mass is 1. So when we add this, it's going to be 170. Okay. So we know that it's 2.6 is equal to N of O2 times 32 by 170. Right. So what is N of O2 now? It's going to be 2.6 into 170 divided by 32. Is it coming? 13.81. Okay, we have quick answers today. So we found out that number of moles of oxygen is 13.81, which is good. Now, how do we find the number of moles of product species? So let's go ahead and balance this. How do we balance this? Now, you need to look into the question carefully. So it has been told that assume that more reactive hydrogen in the fuel is initially oxidized to H2O. So what has been told is the hydrogen is most reactive, so it will fully get converted to H2O. Okay, and the remaining is fully gets converted to CO and thereafter to CO2. Right, first it gets converted to CO, and then if there is a possibility, if there is extra oxygen remaining, then it gets converted to CO2. Anirudh?
Yes, I had a doubt that why did we consider like C12H26 as 1 mole?
Right, so actually it is a compound. Okay, C12H6 is a compound, and how many moles of compound you have is 1 mole. So basically when I wrote this equation, I wrote for per mole of fuel. Okay, so for 1 mole of fuel, how many oxidizer I got, and based on that oxidizer, how many number of moles of product species you are going to have. Okay,
Okay, sir.
so but in a propellant block, let's say, it depends on the size, right? So if your size is bigger, the propellant block is going to be bigger, and let's say the R depends on the mass. Let's say you have a 200 or some 1700 grams of C12H26, then you have 10 moles of C12H26, right? Because 170
Yes, sir.
gram is 1 mole. But what we write here is we will write for per mole basis of fuel. So for 1 mole of fuel to burn, okay, we are interested in fuel, right? So for 1 mole of fuel to burn, how much oxidizer I have, and based on that how much product species I'm going to form. That is what we are seeing here.
So one
Yes.
question.
Mm-hmm.
So can we make the same assumption even if the fuel is a element? Like here you said it's because it's a compound. So even if it is an element like hydrogen or carbon,
True.
can we make the same
Yeah.
assumption?
So still H2 plus O2 is going to give H2O, and this can be 8 also. So still it's so we you it's not going to change the um, flame temperature, for example. So when you consider 2, you are going to have 16 O2 based on the mixture ratio, right? So this is the it's like LCM. If you see, this is the least common multiple you can have for this reaction, right? So let's say your mixture ratio is something like 4, let's say, which means that I don't know how many moles of O2 I have, times I have 32 is a molecular weight, and then N of H2, which is actually 1, because we are always we are concerned with 1 mole of fuel. What is the uh, uh, things you are getting, and all others are just multiple of it. So that's definitely not going to multiply the temperature, but what I'm trying to say is it's going to be multiplied to the mass flow rate, for example. So it's all others are like, you can think it of like intensive. So we are seeing it in terms of intensive. We are excluding the dependence of extent of system based on the uh, uh, fuel. Okay, so for given fuel, for 1 mole of fuel, how many oxidizers I have, and what is the temperature I will reach, and what are the product species I'm going to reach. So that is what we are. You can even do a different analysis. You can even tell I have 2 moles of hydrogen, okay, and my mixture ratio is 4. Then what you have to do is you just need to multiply 2 into 1, or 1 or 2, right? Because hydrogen is a molecule, so molecule is going to have 2 molecular mass. So you just need to multiply 2. You can do anyway, but you are going to reach the same results. That's what I'm trying to say. It's easier when you take 1 mole of fuel. It will be easier when you go forward. You they are Right now you need to multiply 2 when you calculate heat of combustion, when you calculate CP, when you calculate sensible enthalpies. You need to multiply this number of moles for fuel. So that is the reason we usually, it is not an assumption, it's just convenience. So you can even take some 10 moles of hydrogen and you can perform this analysis, and you are going to get the same results. It is not basically an assumption, that's what I'm trying to convey. So does that answer your question?
Yeah. I was just a little confused with it actually.
So to avoid confusion, what I would recommend is you can. So I will solve today with 1 mole of the 1 mole of C12H26, right? So what you can do is you can solve with 2 moles, or let's say 2.35 moles, okay, for example, and do the same analysis. And for your surprise, you will see the same results, because this is how could I put it? So it's like this is the uh, so when you have
So
more
it's not
fuel,
compound dependent. It's not
so
compound dependent.
yeah, it's not how many moles you are using in the fuel side. So basically if you take, but it is going to depend on mixture ratio. You cannot change the mixture ratio. Mixture ratio is going to be 2.6. But let's say okay, it will be clear when you balance this equation. So I will let you know, I will come to this question again, okay. Let's first balance this equation. So we have C12H26 and 13.81 oxygen molecule. So now what we told was, we told that more reactive is hydrogen, right? And it gets fully oxidized. So I'm going to have H2. So this side I have 26 hydrogen atoms, and this side I should have 26 H2O molecules, right? Because hydrogen can easily get oxidized. So then I will be having 13 H2O, right? So is this clear what I'm trying to convey?
Yeah, this is clear. Yeah.
So if I have 13 H2O molecule, now I need to balance. Now what has been given is the carbon present in the fuel is first oxidized to CO, right? So we need to consider CO, and what has been given is it is the carbon present is only oxidized to CO right now, okay. So if we do that, how many CO molecules do we form? So we took 13 O atoms for H2O, right? Total we have 13.81 into 2 O atoms, right? Which is equal to how much is this? I think it's 27 something. 7.62, right? So 27.62 O atoms, right? In that I took 13, right? So remaining would be 14.62 O atoms, right? So remaining I have only 14.62 O atoms, and this O atoms is going to form carbon monoxide, CO. How many C I have? I have 12 carbon atoms, right? So this 14 atoms going to form CO molecule with 12 carbon atoms. So what it does is it forms 12 CO, right? Plus remaining would be 2.62 O, right? This is what it forms, right? So this is what it's been given, right? If you go back, subsequently the carbon present in the fuel is first oxidized to CO. First I'm fully oxidizing CO, and then thereafter CO2. So if some oxygen is left, I will oxidize the CO2, okay. So we do have some oxygen left, which is 2.62. Now, how do we go about it? Now I can have CO2, but how many CO2 I would take? Yes.
Maybe two.
Yeah. Why not 2.62? We have remaining 2.620, right?
Yeah, so what I thought was instead of 12 CO, it becomes 10 CO plus 2 CO2 plus some remaining
So
oxygen.
there will be still remaining. So let's go ahead like whatever you said. It's plus 2 point. Sorry. Um, this you can write it like 2CO plus 2.620, right? Now what happens? It forms 10CO plus 2CO2 plus 0.620, right? Still some
Yeah,
O
yeah.
is remaining. We can oxidize even more, right? Oxidize even more, right? Since we have extra oxygen atom. So how can we oxidize? 10CO plus 2CO2 plus 0.620, right? What I can do is I can write 10 minus 0.62CO plus 2CO2 plus 0.62CO plus 0.62O, right? So what is 10 minus, yeah, 9.38 CO plus 2.62 CO2, right? So now I do not have any oxygen left. So that is what that is what actually told in the question. The carbon present in the fuel is first oxidized to CO and then thereafter CO2. If there is remaining oxygen, we will oxidize it to CO2. Yes, Kaviyara sir. Kaviyara sir, you have any doubts? I think you would. Okay, 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 okay. Then fine. So yeah, we found out it to be uh, 9.38 CO and 2.62 CO2. So maybe we can write this again here. So we had 13.81 O2 and then um, 2.62 CO2, right? And then we found the hydrogen is going to get oxidized more, and then we have 13 H2O, and then remaining 9.38 CO is present. Okay, so this is your reaction. Okay, in general, inside a rocket motor, uh, it doesn't do any balance like this. So hydrogen is there, I will go and react with only hydrogen. So if you take a combustion course, you will know how accurately you can calculate these product species moles, because you cannot do just balance. uh, you have to satisfy second law. Okay, those are little advanced topics, that's why it has been neglected in this course. But if you are interested, you can take a combustion course and you can learn, if I have this much fuel and this much oxidizer, what are the possible uh, product species I'm going to have. So for example, you won't be ending up with only CO2 and H2O and CO. You will have OH, you have H, you have O, you might have OH molecule, right? You can have oxygen remaining, you can have hydrogen H2 remaining, you can have O2 remaining, you can have HO individual atoms remaining. So you will be having more hundreds of species in it. In fact, you might even have aldehydes because it's C12H26, right? So you can have aldehydes in it. You can have particles in it. Those particles are nothing but carbonaceous particles in it. So all these things are, if we we not go into that deep for this course. Okay, so that's why we simplified it and we gave it in the question, like H2 gets reacted first, and then OCO and CO2. Okay, so let's stick to this and then we'll try to we'll solve this problem. Okay, so the first uh, what is it? The first question is solved, right? The moles of all product species, that has been solved. So the moles of CO2 is going to be 2.62, of H2O is going to be 13, right? And the moles of CO is going to be 9.38. This is done. So now the next question is the molecular mass of this product mixture. How do I calculate the molecular mass of this product mixture? I know the number of moles, right? Calculate the molecular mass of this product mixture. Does anyone have any idea?
Yeah, so number of moles times the atomic mass, summation of all those divided by the mean, like basically the total number of moles.
Yeah, basically, if you see it, uh, for example, if you consider C12H26, right? So, how do we calculate C12H26 molecular weight? We calculated it based on this individual molecular mass, right? So, similarly, if you consider this also as a single compound, and if you try to get this, you will be, so let me write it down, whatever you said. So n of,
Sir, whatever she said, it would give us the mean molecular mass, I guess.
so mean, it is not mean molecular mass, it's a molecular mass of mixture. Okay, so it is no more it is not a single compound, uh, like H2 or O2, right? It is a mixture.
Yes, sir, but like, why are we dividing it with number of moles?
So it actually comes from the definition of molecular weight of mixture. So what is the definition of molecular weight of mixture? It's like it's nothing but, how do I put it, so what we know about this mixture, so the mixture mass is going to be same, right? So either you calculate using molecular weight of mixture or molecular weight of individual compound, doesn't matter. But what is the uh, uh, aspect is that the mass is remaining same. However you want to express it, it's going to be different. Let's say for example, you have a mixture. Okay, you have a mixture which contains um, O2 and N2. Do you know what mixture is this? So there's going to be O2 and there's going to be uh, here it might be dimensionally incorrect. So no, Kaviyarsan, if you look at it, this is the number of moles and this is also number of moles. This is only in terms of gram per mole, right? When you multiply these two, what happens? This becomes, the numerator becomes gram. So so the dimensionality is still right. It's mole times gram per mole divided by total number of moles, right? So what you did was you cancelled it and you again got gram per mole. Molecular weight is gram per mole, right? So yeah. Anyway, but if you look at this mixture, air mixture, let's say, so you will have 1 mole of O2 and 3.76 moles of N2. Okay, and do you know the molecular weight of air? It is nothing but you have 21% of O2 and 79% of N2, right? Based on that only. So molecular weight of air is 28.84. So air is a mixture, all right? So can you calculate the moles of this? So you have 1 mole of O2, which is 32, right? Plus 3.76 times N2. What is N2? N2 is 14, right? Is it 14 or 28? 28, right? How much is this coming? This is 32 plus 105.28, which is 137.28, right? So this is the total grams. It's not gram per mole, right? So you calculate how many moles you have, how many moles of each and every species, and you found the total uh, mass of the substance. Now what you have to do is you need to find molecular weight, which is gram per mole, right? So for one mole of, for this mole of mixture, how much gram is there? So how many moles you have? You have 1 mole of O2 and 3.76 mole of N2, right? So you divide it by 1 plus 3.76 and you will get gram per mole. This will be the molecular weight of air. This is how actually you calculate. So let me calculate it for the sake of completeness. Okay.
Understood, sir.
Oh
Yes.
yeah. So it is 28.84, right? So basically, what you are trying to do is you are just expressing this mixture in terms of a single entity, and you are going to express it in terms of molecular weight. So it basically comes from the molecular weight definition. That is how we define a molecular weight. Per mole, what is the gram, right? Similarly, for per mole of this mixture, what is the gram? Since we have O2 and N2, we have we have some certain number of moles. We need to divide that number of moles for the given mass of the system. Okay. So having understood that, let's calculate the molecular weight of this product species. So how do we calculate? Molecular weight is going to be 2.62 times CO2 molecular weight, which is how much is it? O2 is 32 plus 12, right? 44.
44, yeah.
Yeah. Okay. Thank you. So 13 times H2O,
18.
18, plus 9.38 times CO,
30. So
30.
20.
How much is it? 12 plus 16, right? 28. Divided by 2.62, 13, 9.38. How much is it? How much the molecular weight is coming? How much are you getting?
I think it's a 24.4, sir.
Okay. Yeah. So it is actually gram per mole, right? This is the molecular mass or molecular weight of the product species. Okay. Product mixture. Okay. So one thing we found out, one is for to find the C star velocity, we found the molecular weight of the product. Now the second thing, important thing is you need to find the temperature, right? How do we find the temperature? So to find the temperature, what we need to know is heat of combustion, right? How do we find the heat of combustion? By the way, are you guys do you guys understood that how the temperature has been found? Like you must have gone through the lectures. So,
Yeah, I did not understand because I think there was some differential equation mentioned, like in terms of latent heat and everything.
okay, so it is nothing. Yeah, I mean, yeah, adiabatic flame temperature. So uh, basically, what you have to understand is energy can neither be created nor destroyed. Okay, that is the fundamental concept. That is the energy conservation principle, right? Uh, so if you have some energy in the reactant side, the same energy is going to be in the product side, but the temperature would be different, which is important. You need to know. So if you calculate the enthalpy, right? So you might be thinking that enthalpy is nothing but CPT, right? That is what you might be thinking, but enthalpy is not CPT. Instead, change in enthalpy is nothing but Cp times change in temperature. So this doesn't tell you the temperature will not change. So initially you have some fuel, right? C12H26 and oxidizer, fuel and oxidizer you have, and it has some energy in it. And finally you have CO2, H2O, and OH, and it also has some energy in it. And if you compare these two energies, it's going to be exactly the same. Okay. So that is what the first law tells. That is what the first law of thermodynamics tells, and that is what the energy conservation principle tells. Energy conservation is energy can be neither created or not destroyed. Now, if so, here energy we are going to express in terms of enthalpy. Enthalpy is nothing but uh, H, right? So there are two kinds of enthalpy, because one is formation enthalpy, the other is sensible enthalpy. Okay, let me write it here. So this is called total enthalpy. Okay, so total enthalpy is actually nothing but formation enthalpy plus sensible enthalpy. Okay, sensible enthalpy is nothing but what we feel, that is what Cp delta T. Okay, so when we calculate enthalpy as Cp delta T, it's called sensible enthalpy. When there is a change in temperature from 298 to 398, you will feel you will sense it, right, based on the change in temperature. That is what comes here. So basically you will write so let's take this equation, dH is equal to Cp dt, right? Let's say if you integrate this equation, right, what happens? H is equal to nothing but, let's say, 0 to h, or let's say some h of 2h. Okay, it becomes integral of Cp dt, right? Basically how it comes is h is equal to some h of, I don't like, we don't know what is h of now. Okay, plus Cp dt. Okay, in this part is what sensible enthalpy, and the remaining part here is what we call this formation enthalpy. So the basic fundamental thermodynamic equation is this thing. Okay, dH is Cp dt, and if you want to find the enthalpy, because at the end we have to compare the energy and we need to find the temperature, right? So we need to convert this change in enthalpy to a standard enthalpy, right? So further we integrate it. When we integrate it, there is a constant that is nothing but the formation enthalpy. Okay, so we have two enthalpies, one is formation, one is sensible. Okay, and what we have told is this chemical reaction, there is not going to be energy change. Okay, so there is a possibility that the internal energy can be converted into sensible energy, right? Internal energy can get converted into temperature, or the temperature can get stored in terms of internal energy. That is also possible. So these conversions are internal in the sense the formation energy. Okay, these changes can happen, but the total energy will always remain same. So that is how, let's say, if you consider a thought process. Okay, initially I have a box which has C12H26 and then some 13.8 moles of 81 moles of O2. Okay, now at 298 Kelvin, that's what is given in the question also, at 298 Kelvin at standard conditions, I believe. So yeah, see, at standard conditions, oxygen at standard conditions burnt in the rocket. Okay, so at 298 Kelvin I have something. Now I am allowing it to react. Okay, so it can react and it can form all the products it wants. Okay, so upon conversion it forms some moles of CO2, some moles of H2O, some moles of CO, and then I'm telling you that it is a adiabatic. Okay, this is adiabatic, so no heat is released outside. So this is also adiabatic. Okay, but upon conversion what happens, the temperature here is going to rise. This is what we call it as adiabatic flame temperature or the chamber temperature in this case. So why it is going to rise is because of this change in the formation enthalpy. Okay, the sensible enthalpy affects little much this adiabatic flame temperature, but the C12H26 has lot of chemical energy in it. That chemical energy is represented by the formation enthalpy. Okay, and that formation enthalpy is very high in terms of C12H26, and it is low in CO2, H2O, and CO molecules. That is the reason this big enthalpy, formation enthalpy, gets converted into a sensible enthalpy in the product side, and this sensible enthalpy give rise to increase in the temperature. Right now, you stop here. You take an you what you do is you keep on removing heat from this. Okay, in the process, I will remove some heat Q. Okay, and then I will cool this down to 298 Kelvin. Okay, I started with 298 Kelvin, and then I again reached 298 Kelvin. Okay, now I removed this heat, right? This removal of heat is nothing but heat of combustion. Okay, how much heat you can remove from this heated products is what heat of combustion. Okay, so basically, then, so let's say if you want to calculate heat of combustion, then how do you calculate heat of combustion? It is nothing but combustion H of products, right, minus H of reactants, right? So finally I have H of products. Okay, and then initially I had H of reactants. So finally I have some energy of products, and initially I have energy of reactants, and going to remove heat while I converted, right? So in this process I didn't. So during this process I didn't remove any heat, and while during this process I removed heat, right? So what is that much heat is what you want to find. It is going to be nothing but energy change you have, right? So here what happens? Energy of products, and provided both are in same temperature. And this is also at 298 Kelvin, and this is also at 298 Kelvin.
Sir, as we are removing the heat in the second, so sir, this H product minus H reactant whole should come negative.
Yeah, you are right. So in order to make it positive, we multiply negative sign in here. So basically, you are taking heat, right? If you are taking heat, it should be negative, right? So adding heat is positive, taking heat is negative. That's why we had a negative sign.
Yes,
So,
sir.
if I have to understand this adiabatic flame temperature, what is being asked is what is the temperature equivalent to this heat removed? Is that
Exactly, exactly, exactly.
okay?
For that, you need to know how much heat is removed, right?
Okay, okay.
So that is why we calculate how much heat is removed. Then what we do, actually, this is a little, there is an easier way, but this is what has been followed in the course, so I'm just following it. If you have time after the class, I can explain you an easier way also. But so you find how much heat is removed, and then you go back to this state again. Okay, right? So but now this heat is only added to increase the sensible enthalpy. So here if you look at it, these enthalpy, see, it's at 298 Kelvin, right? So these are formation enthalpies. Formation enthalpy, we can call it, we know it to formation of products, right, minus H of formation of reactants. It actually tells the measure of how much chemical energy we have in this system, right? So let's say if we want to calculate this, what are the let's say if I want to write it in terms of product species and reactant species, I have summation of I, Ni. We can write H bar because it's in terms of per molar basis. Okay, if it is per mass basis, you can write H. So it's just the convention. Okay, minus. So this is going to be products, and similarly we have reactants, which is nothing but propellant. Ni H bar Fi. So now here one we wrote only HF because there is no change in temperature when we go from state 1 to let me write it, this is 1, this is 2, and this is 3, right? When we went from state 1 to state 3 without considering what happened inside, if you just consider two states, so because in thermodynamics we deal with states, uh, if you consider just these two states, there is no change in temperature, which means sensible energy didn't change, but there is a formation enthalpy change. So since there is a formation energy change, because of that you removed some heat, right? So we removed some heat. That heat is what we are going to calculate. That's why there is no Cp term in this equation. Okay. So let's say if we calculate that, what is the, okay? Did I give? So heat of formation is given. Okay. So heat of formation of CO is 390. So basically N of CO, HF of CO plus N of H2O, HF of H2O, and 2 HF of HCO2 minus N of C12H26, right? HF of C12H26 plus N of O2, HF of O2. So for the elements, you see, elements at naturally occurring state, like for example oxygen is going to naturally occur as a gas, right, at the standard conditions. For that the formation enthalpies are zero, so that's why uh, uh, we can take formation enthalpy to be zero. So these are tabulated values. You can take it from the literature, or it has been found experimentally. Okay, so if we try to do this, so this will give you how much the delta Hc is needed combustion, right? So maybe you can I have enough time, but what we will do is you can find this value. Okay, uh, if I have, I can give that value also. So this is how we calculate it. So you can check this. It is around 5632.75 into 10 power 3 joules. Okay, so here this is joules per mole, this is joules per mole times the number of moles we multiplied, so we end up getting joules. Okay, so this is the amount of heat I am removing from the system. Okay, now I remove this much heat. Now this heat is only used to raise the temperature of product species from 298 to some adiabatic flame temperature. Now how do we do that? Okay, so now Q here, which is delta Hc, which is nothing but it has to raise, let's say if I write it in same format, here I write H sensible. Okay, it has to raise this energy of products to the 298 Kelvin. Why didn't we consider reactants here? In fact, we should consider reactants, but we no need to raise the temperature of reactants because it's already at 298 Kelvin. Let's say for example, if you take hydrogen and oxygen, it is at very lower state. You always need to bring that up to 298 Kelvin because all the formation enthalpies are defined as 298, defined at 298 Kelvin. That is the reason we move the datum to 298 Kelvin. So in order to take hydrogen and oxygen, which is at very low temperature, to the 298 Kelvin, we had to give some heat, right? So that heat we need to give, and upon conversion, right, we removed some heat, right? That heat should be subtracted with this heat, and it will give you the adiabatic flame temperature. Here in this case, it's sensible, right? Here in this case, what happens? This is 0 because my reactant is already at 298 Kelvin, right? So you no need to raise the temperature of reactant to a initial temperature, right? Before, what is my initial temperature? Let's say, for example, uh, in this question, instead of giving standard condition, if I say my initial is 300 Kelvin, then I need to raise my mixture from 298 to 300 Kelvin. For that, I need to give some heat input. That heat input, I need to subtract it from whatever heat output I get upon completion of this reaction. So it's just the balance, it's just calculation you need to do, right? So I hope it's clear. So here, if we do it, let me write it out separately. Again, I have N of CO2 plus H sensible of CO2 plus N of H2O plus H sensible of H2O plus N of CO plus H sensible of CO, right? So these are the things. How do I write H sensible? I know it's nothing but C integral of CpCO to dt. And what I'm going to do, I'm raising the temperature from 298 to some adiabatic flame temperature, right? So from 298 to some adiabatic flame temperature, which is Tc. Then plus NH2O integral of CpH2O dt from 298 to Tc. Similarly, NCO integral of 298 to Tc Cp of CO times dt, right? So this is nothing but this Q. What we found, Q is to be 5632.75, right? 5632.75 into 10 power 3 joules. So now we will assume Cp to be constant. For example, I will give you the Cp here. Yes, Anirudh, you have doubts?
No.
Okay. So I have few CPs here, okay? Cp of H2O. Now you need to note something very carefully, okay? I have a gas Cp because H2O can remain while moving from 298 to higher temperature. What I have to do is I need to, H2O remains as liquid, right, at 298. I need to raise its temperature to 373 and make it gas, right? So then I need to give some heat in order to evaporate it, latent heat, right? So which we call it as HFG of H2O, which is nothing but 40 kilojoules. So I'm sorry, these are kilojoules per mole Kelvin, 40 kilojoules. Okay, so now we need to plug it in appropriately. So let's say, for example, NCO2. NCO2, there is no problem. CO2 exists as gas into Cp of CO2. Okay, Tc minus 290. We already know
Excuse me,
moles.
sir.
Yeah, yeah.
Sir, like as you said, the heat, the total heat is equal to heat of like heat formation
Sensible.
plus
Okay.
sensible heat. So why are we equating the sensible heat with the heat of formation?
Right. So basically, how are you getting that heat? Right. So how do you
Yes.
get the heat? It is due to the change in the chemical energy within the fuel. Right. The fuel has high chemical energy, and the product has low chemical energy. Right. This change in chemical energy doesn't lead to increase in temperature. This change in chemical energy is a heat input, which increases the temperature. Okay, that's why whatever the change in chemical energy we have, that is given to raise the temperature of the products. Okay.
Okay, sir, understood, sir.
So let me quickly complete this. So this one this one you should take it little carefully, because you cannot constantly rise from 298 to Tc. What you have to do is you need to go step by step. N of H2O to Cp, sorry, should be integral of CpH2O. Initially it will be liquid from 298 to 100 degrees Celsius, let's say 373 times dt plus, uh, let's write it outside, moles is going to remain same, right, within this, plus h of g, which is latent heat, which is also energy you need to give to in order to evaporate, plus from 373 you need to raise it to Tc. And now the Cp has changed because it's in the gas phase. Now there is another Cp. Okay, so let's say if I want to simply write this equation again, 56.32 into 10 power 3, I think it's 5632, is equal to, so I will have carbon monoxide, carbon dioxide, both are going to be in gas phase in both 298 and in combustion chamber temperature, right? And then carbon monoxide is all going to be Tc minus 298, right? Now I have N of H2O, where I'm again assuming Cp to be constant, and I'm telling Cp of H2O of liquid, okay, times 373 minus 298, right? You are just integrating. It's like Cp comes out, so integral of dt is just t, and you apply the limits here, and then plus h of g, which is nothing but 40 into 10 power 3, plus Cp of H2O gas, um, uh, so Tc minus 373. From 373 to, you are raising it to Tc. Now the only unknown is Tc, so you will find Tc. Okay, you can do this calculation, and for the sake of completeness I will give you what answer I got. So I got something like 4311 Kelvin. Okay, so now you have obtained Tc, you know molecular weight. You, how do you calculate? So you need to find C star. What we know about C star? C star is nothing but 1 by capital gamma square root of R naught Tc by molecular weight of the product species, product mixtures, right? So what we know is, we know this, we know this, we know this. The R naught is universal gas constant, but we don't know this, right? Gamma. Gamma is a function of small gamma. Small gamma is nothing but Cp by Cv, right? And what is Cv? Cv is nothing but Cp minus R naught. So all these are molar bases. Okay. So Cp minus R naught, which is also universal gas. Only thing is you need to find is Cp. Now you need to find Cp of product mixture. How do we find Cp of product mixture? Cp, if you don't know how do you weigh it, what you can do is you can see what is the unit of Cp, which is nothing but joules per mole Kelvin. So per mole, how much energy I need to raise for 1 unit in temperature, right? That is what Cp is. So then what you can write is, you can write Ni of Cpi. Okay. So you know individual species Cp, you know number of moles, so you can find Cp of product mixture. Once you find Cp of product mixture, you can find Cv of product mixture. Once you find Cv of product mixture, you can find, go and find gamma. If you find gamma, you can go and find capital gamma. Now the equation becomes complete, and you can go and find C star velocity. Okay, so this is how you find it. Okay, I took extra 3 minutes, sorry for that, but uh, I couldn't do these calculations also, but I just gave you the uh, way how do we calculate it. So do you have any doubts in how did we do it?
Yeah, the last step I think I did not follow, sir. The where
Yes, the C
my
step.
yeah CP of products.
Okay, so this C star velocity we know it is gamma, right? If we have gamma here, right? We have uh, we have R naught, we have Tc, we have molecular weight of products, but we don't know gamma. In order to find gamma, we need to, gamma is nothing but Cp by Cv. So we need to find Cp, we need to find Cv. Cv is nothing but, you can calculate it from Cp. Now how do we calculate Cp? That is the question, right? So uh, Cp, we know Cp of individual species. For example, we know Cp of CO2, we know Cp of H2O, and we know Cp of CO, right? And all these are expressed in terms of joules per mole Kelvin.
Okay, so I think it's just the CP times the number of moles, is it
Yeah,
like that?
yeah. So you need this much. One second. Yeah, yeah. So I think you got confused, no? So they should be weighted by mole also, right? So yeah, to take into account
Yes,
the,
sir.
yeah. So is that what your confusion is? I forgot. I missed this
Yes,
denominator.
sir.
So yeah, basically, whatever we did for molecular weight is gram per. So we multiply the number of moles, and then initially inside the mixture how many moles we have, we divided it. Similarly for CP also, we need to multiply n times everything. So for example, in order to avoid confusion, I will write it: Cp of CO2 plus n of H2O, Cp of H2O plus n of CO, Cp of CO divided by n of CO2 plus n of H2O plus n of CO, right? So if we do this, basically you need to find a mixture CP, and in the mixture we need to weight it using number of moles. So we have one.
So there's a doubt, sir. So there are two CPs of H2. So which one to take?
See, in the product species at the end of combustion, right? At the end of combustion, will you have gas or will you have liquid? Gas. So you need to take CP of gas. At the end of combustion, what is the, so basically you think where we apply this formula. We apply this formula inside a combustion chamber. So inside a combustion chamber, this is not the process you are going to go forward, right? There's going to be simultaneous conversion of CO2 and there's going to be simultaneous release of HQ. This process is just for you to calculate the adiabatic flame temperature, okay? But this is not the process through which it goes. So this this is this is calculated inside a combustion chamber, okay? From combustion chamber the products are coming out, and that product is going entering the nozzle, right? So if you want to characterize the combustion chamber, you need to find out what is the molecular weight of the product species at the end of combustion, right? So at the end of combustion you are going to have gas, so you should take Cp of H2O, that's all. And in this reaction, this is actually in terms of gas only, right? So this is at 298 Kelvin. These are at Tc, some 4,300 Kelvin, right? At this temperature, you have Cp of gas. All these are gases only. So you need to take gases. Okay. I hope it's clear. And there's one more question. Uh, how do we find Cv? Okay. So once you know Cp, uh, this relation, right? Cv is nothing but Cp minus R naught. Is nothing but universal gas constant. But one thing you need to know, but it is not very important here. If the Cp is given in terms of kg Kelvin, so joules per kg Kelvin, right? Right? Then this is going to be R, where R is nothing but R naught by molecular weight. So you need to take that into account in order to match the units. Okay. So, but here it is no need because everything is given in terms of molar basis, so you no need to worry about it.
So, sir, can this be shared immediately after this? Because I think this will be very helpful for this week's assignment. So, if you can
Yeah,
please.
yeah, sure, that is not a problem. I will share it. So you have the access to the Google Sheets, right? There will be a sheet which has YouTube links and Drive folder links where you can revisit these
Yeah,
lectures. Yeah,
yeah, I have. Yeah.
yeah, yeah. So you can go and revisit it. So if you are interested, okay, know whether everyone is available, but if you are interested, I can give you a simpler way to solve this to find the temperature. Okay, so will you guys stay for 5 minutes if you are interested?
Yes, sir.
Okay, so instead of doing all this, okay, so you converted into product and you removed all the heat, right? And then you found heat, and then you raise the temperature to TC, right? Instead of doing it, let's not come to third state and then go back to second state. Let's see from first to two state. Let's go only one to two state. Okay, so what we know is, we know that energy is conserved. That is clear, right? That is universal, you cannot violate it. Okay, so total enthalpy is conserved. Okay, H of reactants is equal to H of products. You need to note that it is a constant pressure. That's why we are telling in terms of H of reactants and H of products. Okay, so we do not really see, it's just chamber is at one pressure only, and it is going to, yeah, it's constant pressure process. That's why H reactant is equal to H of product. Okay, and you need to note that this is total enthalpy. And what did I say about total enthalpy? It's nothing but formation enthalpy plus sensible enthalpy of reactants.
So could you come again? H reactants equal to H product.
So, can you repeat?
So could you come again on what is H reactants equal to H product?
Right.
Like I
So,
didn't understand.
okay. So, you considered this as a pressure system, right? So, what is the first law of thermodynamics? So, if you go back, it's going to be D is equal to Q minus W, right? This is the first law of thermodynamics. In fact, it's going to be del Q minus del W, right? This is the first law of thermodynamics. It's
Yes.
nothing but change in internal energy is the heat added and then work done by the system. Now, we know there is only one work done for this simple compressible substance. So, dE is going to be del Q minus PdV, right? Now, take this to other side. dE plus PdV is equal to del Q. Okay? Now, it's a constant pressure process. So, basically, this E is nothing but internal energy. Let me change it to U, okay, so that it's clear. Now, for a constant pressure process, which means I have a piston cylinder arrangement, and if as the pressure increases, I will just move the, like it just automatically gets moved, so that pressure is maintained constant. Okay, for a constant pressure process, okay, du plus, you can take P to be inside, PV is equal to del Q, right? So then you can write U plus PV equal to del Q, where U plus PV is nothing but TH. Now, what we did was, we told that it is an adiabatic system, right? So there is no heat added, which means dH is equal to 0. So change in enthalpy of this system, whatever system we are dealing with, is 0, right? Which means H at first state is equal to H at second state. Okay, so which means
Understood.
H at first state is actually H of reactants, and H at second state is actually H of products. Dealing with sensible or formation, not separately. Okay, total energy. So that it simplifies our concept, because energy is neither created or not destroyed. I'm going to balance only the total energies. Okay, so then if we go ahead with this, H of formation, right, all are in per mole basis, and H of sensible by products. Okay, this is true, right? And what we know about H of formation, N of C12H26, HF of C12H26 plus N of O2, H of O2, right? So basically these are nothing but summation of Ni's H F plus Hs, right? So this is, both are same. So basically I just wrote in terms of it. So okay, let me write it in terms of that. It's not a confusion. Summation of Ni H bar, okay, H bar, yes, this is for reactance. Summation of Ni H bar F H bar S is for products. Okay, till now clear, right? Now you have, what are the reactants you have? C12H26, right? And O2. Now let's write it. N of C12H26 times H of formation of C12. Now let's not go into formation right now. Yeah, we already wrote. So H of C12H26 plus H sensible C12H26 plus N of O2 H of formation O2 plus H sensible O2 is equal to products. What are the products? CO2, HF of CO2 plus H sensible of CO2 plus N of CO, HF of CO plus H sensible of CO plus N of H2O, HF of H2O plus H sensible of H2O. Okay, that is all we have. Now that's all. This is the equation you need to solve. In fact, this is the only equation you need to solve in order to get the temperature, and I'm just expressing in terms of formation and sensible. Okay, so let me go ahead one step further. Okay, uh, N of C12H H26, which we already know, 1 times HF of C12H26, which is given, right, plus we need to raise the temperature, right, from uh, so initial temperature is given, right? Initial temperature is 298. Let's say for example I have initial temperature to be, so now if I have 298 Kelvin, how does this H of reactance will happen? So I will always raise the temperature from 298. So from 298 to 298, Cp of C12H26 into dt, which will be 0, right? So I no need to raise any temperature, I no need to give any input to raise the temperature, right? And then plus N of O2, O2 is some 13.81 we have, and HF of formation of O2 plus integral of again Cp of O2 dt, but since my initial temperature is 298, I don't need to worry, this is also 0. Okay, this is my H of reactance, or you can say LHS of the above equation. Okay, so first you can calculate this, you can calculate H of reactant and you can substitute it here. Let's say if you want to write RHS, N of CO2, I think something around 2.65, HF of CO2 plus sensible, right, Cp of CO2 dt, the same thing. And here also you again rise from 298 only, you don't care what is my initial temperature, but you always rise from 298 because my formation enthalpy is defined at 298. That's why, that is the only reason we do that. Okay, to a higher temperature. Okay, similarly we have 13 H2O, HF of H2O. Now this HF of H2O, you need to be very clear whether it is given for gas or it's given for liquid. Usually it is given for it would be given for liquid, and the latent is specified. So if the latent heat is specified and it is given for liquid, you need to take care of all the energies. So basically you wanted to raise the temperature to 2 adiabatic, right? So initially you have some formation energy plus of liquid, and then you raise the temperature to evaporation point, Cp of H2O liquid dt, I'm just writing in terms of integral, but Cp is constant. You can take it and write in terms of, you can just write Cp delta t. Okay, and then plus h of g plus integral of some 373 to Tc. So it is basically how much energy you need to raise the temperature. That's all, and that energy is given by the reactants in the reactant side. Okay, then plus I think some 9.38 or something HF of CO plus integral of 298 to Tc Cp of CO into dt, and this will be equal to whatever the H reactants we have. And you solve this equation, you will directly get uh, uh, the adiabatic flame temperature. You no need to calculate heat of combustion, and you no need to calculate LHS is not zero. See, you have formation enthalpies, right? Your formation enthalpy is remaining, right? Formation enthalpy of C12H H26 is not zero. Formation enthalpy of O2 is zero. That is true, but C12H6 is not zero, right? It's like chemical energy for the reactant. So I have a fuel, and it should have some energy in order for it to react, right? So here H of reactants is not zero. C12, yeah, HF of C12H H26 is not zero. It's actually given in the question. So we have 5 minus 159 kilojoules per mole. So you no need to calculate exactly heat of combustion. So once you instead of calculating heat of combustion and then calculating this sensible enthalpy change, you can just stick to the first principles, which is just H of reactants is equal to H of products. And H of reactants you express in terms of formation enthalpy plus sensible enthalpy, formation enthalpy plus sensible enthalpy, and you keep doing it, you will end up getting the adiabatic flame temperature. That help? Uh, Instead of confusion, this might be, I think, better way.
Yeah, I mean, I can understand now, but the problem with this entire week six is like it seems easy, but then I think once we go back and look, it is it's very difficult to comprehend and follow through.
Okay. Yeah, yeah, it is true because uh, there is a lot of combustion aspect has been compressed and given in this week six. Combustion itself is a separate subject you need to learn in order to know just the fundamentals, right? So it is it is just vast area, you cannot easily uh, grasp it within few lectures. So, but professor did a very good job in trying to reduce it and give it to you. But the subject is like that. So if you want to conceptually understand, let me write this. Okay. Um, so this is energy. Okay. You see it as a energy or enthalpy. Okay. Just drawing a bar chart. You all know what is bar chart. Okay. And there is another bar chart. Okay. So So this is reactants, or in our case it's a propellant C12 H26, and then O what is it, O2, right? In that, if you see, there will be lot of chemical enthalpy. Okay, so it's like just balancing the, like we always deal with balancing, right? Like we have 100 rupees, we give 5, we will give 10, and then we will take 10, we take 5. It's like same only, just we need to balance it. So this thing, okay, this is formation enthalpy. Okay, okay, and then remaining we have is going to be sensible enthalpy. So in our case, this sensible enthalpy is 0 at the reactant side because we are at 298 Kelvin only. If I have, let's say, some 600 Kelvin, my initial temperature is 600 Kelvin, let's say, then I need to raise the temperature, right, from 298 to 600. At that time, this sensible enthalpy comes into play. But I am drawing it for more general case. Now, I have this much energy, okay, okay, this much energy, total energy is this much. Some are sensible, which I could feel. Some are chemical, which is present within the fuel, which you cannot feel, which will be felt only when there is a reaction happens. Now this energy is same as in the product side, but the shift is different. Look at it carefully. In the product side, you are going to have very less enthalpy and very high sensible enthalpy, and that is the reason you are having very high temperature. Okay, so reactants at 298 Kelvin, and it has formation enthalpy and that's some sensible enthalpy. Now I converted into products. My formation enthalpy is less because products formation enthalpies are less, and if I want to have equal energy, I should have equal energy, right? Because it's a, you cannot violate energy conservation. Energy is always, energy can neither be created or destroyed, right? So energy can only get converted. Now what I did is I converted this formation enthalpy into a sensible enthalpy. Since my formation enthalpy of products is less, remaining all is sensible enthalpy, and that is the reason I can have a very high sensible energy, and that is the reason I can feel it, and that's the reason I have a very high temperature. So basically, this is the concept. We use it to find this adiabatic flame temperature. Okay, so basically what we did H of reactant to be H of products. So these are products. This is the underlying concept through which this whole formula is derived. This energy is getting converted to this energy. You just need to balance it somehow, and you need to get the temperature. That's all. So does that give you a better idea?
Yeah, this is really helpful, sir. Yeah, very helpful.
So basically, energy, that's what you need to remember. You just need to remember first principles. Energy is conserved. That's all. If energy is conserved, I should balance it and get the temperature. That's all. So initially I have this much energy. Later I have this much energy. But the composition of each energy is changing. Because of that, I have different temperatures. That's all. So there might be some questions in week 6, I suppose, which can, let me have a look at it, which might have a higher initial temperature, right? At that time, you need to take care of it. That's all. So this carbon powder is at 25, no problem. Okay, okay. I think it. Uh, okay, I think it's less complicated, I guess. So yeah, but the basic concept is this. All the things what we do, we just need to implement mass conservation, energy conservation, momentum conservation, and everything is going to come out. That's all in this, whatever we do. Right. So, do anyone else have any more doubts? So, if the reactants are at low temperature, we have to add it to bring it to STD. So the same thing. So if you look at this equation, you can just go ahead with this equation, right? So what I will have, I need to so from 298, right, I need to go to, let's say, 40 Kelvin is given. Okay, then what happens, this 298 becomes 40. So at that time what happens, when you write Cp is equal to Cp of C12H26 into 40 minus 298. So at that time this whole sensible term will automatically come negative, which gets taken care. That's all. So you need to start from 298. 298 is the base, and this is initial temperature. um, Maybe that I can give a Maybe I can write that as a general formula. Okay, so sorry for taking a lot of time, but uh, it should be h of I plus integral of 298. This doesn't change at all. Okay, and then t initial. Okay, and then Cp of I dt. This is for reactance equal to summation of products Ni h of I plus integral of again 298. You are not going to change the datum and raise it to adiabatic flame temperature Cpi dt. So this is the equation. You just need to follow it in order to find the solution for this. Is that clear, Zaman? Kapit Zaman. I'm repeatedly pronouncing your name very badly. Sorry for that. Okay, so can you suggest one book which will be helpful throughout the course? Um, yeah. So one of the book is by Rocket Propulsion by K. Ramamurthy. The same professor. I actually have this book. If you can have a look at it. It's in Amazon also. So this book is fully about. Okay, so this book is it covers whatever taught in the course. But if you want to have a more detailed understanding on rocket propulsion, there is one more book called it's called Sutton, Robert Sutton, I guess. Okay. Rocket Propulsion Elements by Sutton and uh, Biblas. So you can try that also. Rocket Propulsion Elements. So this is also a good book. Um, but in fact, if you see the field of rocket propulsion, it is a combination of lot of things. One is fluid mechanics and combustion, right? And there's going to be multi-phase flows. So everything you cannot go in detail in one book, right? So in fact, if you want to have a detailed understanding of combustion, you need to study another book called Turns, Stephen R. Turns. Okay, Combustion, Introduction to Combustion by Stephen R. Turns. In that book, it is clearly explained how this adiabatic flame temperature will be calculated and what is the concept behind this adiabatic flame temperature. Okay.
Sir, do you have a PDF of Ramamurthy sir's book?
I do not have the PDF. I have the book with me. That's all. Do you? I think there would be a notes something in the NPTEL itself, right? So, but I think that would be different, is it? There is one English book. The in your portal. I think that is something else. I do not have the PDF. All right. Does anybody else have any more doubts? So basically, I've gone through the quizzes. I think you need to calculate CPs, you need to calculate the number of moles, and you need to calculate flame temperatures. So that's why I made one question which has everything in it. So based on that, I get C star velocity. You can go and check that also. I think I got C star velocity to be around 18, 1867 something meters per second. So you can uh, complete this problem and you can check for yourself.
So this also will be shared in the Google Docs, right?
So basically, yeah, I will just directly upload it in the drive. You can go and download it.
Okay.
Thank you, Zaman.
Thank you, sir.
Thank you, sir.
Yeah,
Thank you so
yes, right.
much.
Thank you. Actually, you no need to call me sir. You can just call me Ganesh Kumar. No problem.
Okay. Thank you, Ganesh.
All right. If there are no more questions, I will stop this. Stop this sessions. Thank you for attending. Hi, Mohammed. Didn't.
Hi, sir.
All right. Do you have any questions, Mohammed?
It's fine, sir. Thank
Okay.
you.
Okay. 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 Everyone. Thank you. We'll meet next session.
Okay.